I hope everyone's having a great day. I'm Mr. Ish. Thank you for joining me for this video. We're looking here at a good concept video on inflection points, where we're developing a framework and understanding of what an inflection point is. We'll start here by looking at the first derivative test. When you're looking here at a specific function, both of these are f of x functions. They're continuous over that interval a and b, and of course you can do a derivative over the items, the x values over a and b. When you're looking here at this first case, if you look from interval a to b and you pick out some of these points and you pick just arbitrary number of points and you draw tangent lines, I'm drawing rough tangent lines only right here. When you look at the rate of change of each of these tangent lines, you know you have a negative in terms of a slope of a tangent line. Here would be negative, here would be flat, so it's 0. Here it would pick up and become positive in terms of the rate of change, the instantaneous rate of change. Likewise here, when you start picking up points and you do these tangent line determinations, here you have a upward and a flat, then a downward, and then a downward. You'll have a positive, you'll have a 0 instantaneous rate of change. Here you'll have a negative, here you'll have a negative. We're seeing that a specific behavior is coming into play. If you're looking at the first order derivative for a function that's continuous and it changes in the following way, if it changes here as you're seeing in this first item from a negative up to a positive, you're looking at what can be indicative of a relative minimum or a local minimum in terms of a extreme value behavior effect. When you're looking here at this specific graph, you're seeing a change from positive to minus, and here you're seeing something like a relative maximum or a local maximum come into play. This right here is the first derivative test. It gives you a good idea of this specific presence of a relative or local minimum or max. Also keep in mind, when you're looking at the first order derivative for a function, if the first order derivative is larger than 0 and if the first order derivative is less than 0, you know, if the first order derivative is greater than 0, or that is you have positive values, you're looking at upward sloping tangent lines. If it's less than 0, you're looking at negative tangent lines, which are in terms of their slope downwards. This right here indicates that you have a function that's increasing. This here would be an indication of a function that's decreasing over that interval. So always keep that in mind. It's logical and it's obvious, but you can keep that in mind. But with regards specific to these changes I've addressed with the relative and the local minimum and max that you can predict, also note the following. You can have instances such as this, where you have a curve which will look very much like this, or a curve which looks very much like this. If you were to pick out points from the interval right here, and let's just identify them as arbitrary points and we draw tangent lines, you could have tangent lines here which are positive, here you could have a 0, here you could have a positive or positive, but you're not seeing a change from a positive to a negative. Right here you could have a situation within a given interval for a continuous function. You can have the following play out. You have a minus, a something. Both of these instances are something close to a 0. Here you have a minus and a minus. In both of these instances, you're not seeing that change from a minus to a positive or positive to minus. So keep in mind that there are instances where that first derivative test does not accurately come into play, and in this instance you cannot predict the presence of a local minimum or local maximum. You cannot, because you're not seeing that expected behavior of a positive to a minus shift or a minus to a positive shift with regards to the first order derivative. And you would clearly say that in that specific instance that you have no local minimum and no local maximum. Now let's shift gears towards the second order derivative and how that helps us in terms of the behavioral patterns. If you were to look at both of these and you were to pick out some points over here, and we'll pick out 3. When you look at this first depiction here and you start drawing tangent lines, you see you have one here, you have one here, and you have one here. When you try to draw a tangent line over here, and you know what the definition of a tangent line, it grazes your function or a curve at a specific point, like a line which barely grazes it. There's your tangent line, here's your tangent line, here's your tangent line. What difference do you see? In this function I'm seeing that in terms of the relative location and perspective here, the function is above your tangent lines, is above the tangents. Let's just write that. And in this specific instance, I'm seeing that the tangents are above or superior to your function. Here your function is superior to your tangents or above. Here the tangents are superior or above the function, and the function is below. Here the tangents are below. This here is a good behavioral trend to notice, because when you're seeing something like this, you're seeing some function which is going concave upwards. You have to know that it's going concave upwards, which means there's a concavity developing and the concavity is pointing upwards. In this instance, your function has a concave or a concavity that is going downwards, and you can even look on your graph and you'll see that the concavity points downwards. What exactly is a concavity? It's like the U-shaped portion of a curve. It can either be upwards or it can be downwards, and that's exactly what you're looking at. When the function is above your tangents, you have a concavity which is upwards. When your function is located below the tangents, then you have a concavity that's downwards. This concavity test that we're talking about has very much to do with the second order derivative of a function, and you should know this specific instance over here. The second order derivative, this is right here, f second order greater than 0, and then if f second order derivative is less than 0. What is greater than 0, less than 0 means? It means in terms of a value plugged in, you're getting a negative output or you're getting a positive output. For all the values of x in that interval, as you're judging this specific concavity test, if this is your instance right over here, greater than 0, you have a concavity that's going to be pointing upwards. And that's exactly the situation over here. For the second order derivative values, as you're plugged in, you're getting negative outcomes. You're looking at something that's a concavity that is downwards. And you will remember this from the extreme value videos, because this right here, concavity upwards, is hinting towards what? It's hinting towards a relative minimum. And this right here is hinting towards a relative maximum. Just like the first order derivative test can allude you to that or clue you into that, so can this specific concavity test over here. And of course, all of this is to do with your critical point values. You can say at a specific value c, you're plugging the c right here into these areas of x, and you're having this behavior come about. You can very well utilize this. Remember, look at the relationship of the function and the tangent lines in both instances, and look at the trend as you see, whether it's upwards or downwards. You know this very well would be continuing from something like this. A relative minimum has developed, and this very well would be continuing in this direction, a relative maximum here on the top. At the very peak of that critical point, you know, at the very peak of both, the peak or the zenith of both of these in terms of the actual critical point here, you know, when you put your value into your first order derivative, you have a 0. You know that to be the case because the first order derivative showed you what critical point existed, because at that specific point either derivative did not exist, but if a derivative did exist, it gave you a horizontal tangent line. The second order derivative helped clue you into the fact whether it was a relative minimum or relative maximum by means of this behavior here with regards to changes in your curvature. Now, given that background, let's specifically talk about an inflection point. An inflection point is a certain position or a point on your curve, a point P on that continuous function where the curve will change its curvature. It changes in such a way that you're going from concave down to concave up, or you're going from concave up to a concave down. Let's look at this very first part, concave down. It was a curve which was concave down, and then it has changed to a concave up. Here's my concave down, CD. Here's my concave up, CU. Let's look here at example in terms of the B. We are going change from a concave up to a concave down. Here's my concave up, it's pointing upwards. Here's my concave down, it's pointing downwards. But there's a specific point somewhere on this function within the interval. Interval can very well be from here to here, here to here. There's a specific point right here in between, this transition point between one to the other, where this effect is noted. And how is that effect very well addressed? It is very well addressed by this statement right here, where the second order derivative changes sign. And that's something you have to determine here. Where is that change in sign? And you know the change in sign is either from a positive to a minus, or it's from a minus to a positive. But where that change occurs is exactly where the inflection point will exist. And you have to be able to determine the inflection point. This right here is just giving a general idea of what is happening at an inflection point. But you have to be able to numerically determine what that inflection point is. The most important part of this entire screen is CD to CU, CU to CD. But the fact that the inflection point is where the second order derivative will change its sign. I want to present an example where we talk specifically about this, and it would be a good example, and I want to show you how this comes into bearing mathematically. And let's bring you that example right here. We're looking at a function f of x is equal to sine x. and I'm looking at everything here from 0 all the way up to 2 pi. And what will our curve look like? And we're going to go by 45s. Here's 0, here's pi over 2, and I'll add the 45 degrees momentarily. Here's pi, here's 3 pi over 2, and here's 2 pi. You know the highest point is at a 1, the lowest point is at a -1. Here's my 45, 45, 45, 45, 45, 135, 225, and 315. Our goal is to identify concave up, concave down portions and determine an inflection point. Remember, at the inflection point, your second order derivative of that function will change sign. I'll just write it as this. It'll change a sign, and that's what we have to determine. Let's graph out the sine x from 0 to 2 pi. When we're looking here, you can do the first order derivative test, and you see you'll have positive tangent line, it'll be flat here, negative, 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 negative tangent lines, and it'll be flat here, then positive. That'll only tell you that from the change here, and I will erase this. Here, looking only at the first order derivative, using the first order derivative test, from this point I'm seeing a transition from positive to minus. Here I'm seeing a transition from minus to positive. Here I should have a relative maximum, here I should have a relative minimum, and I do have that. That's the first order derivative test at play, but I'm erasing that because I want to talk about inflection point. When I'm looking at this function right here, what's the thing that I want to do? I want to start determining the derivative of the function, and we'll do that. The first order derivative of this function is a cosine x. But the second order derivative is going to be a minus sine x. You can do your critical point determinations if you want to do cosine x is equal to 0 and x is equal to inverse cosine of 0, which is 2 angles here. In this interval there are 2 of them. There's pi over 2 and there's 3 pi over 2. That tells you pi over 2 right here is a critical point, here's a critical point. We know if you actually plug in this pi over 2 and 3 pi over 2 right over here, in the second order derivative you'll have a minus sign of a pi over 2, you'll have a minus value, and this tells you based on that minus outcome from that you have a relative maximum, because the relative maximum exists if the second order derivative test placing the x-axis value of the critical point gives you a negative. But when you put the x-axis point of the other critical value, which is a 3 pi over 2, you have a minus, minus, you get a positive, and that positive here tells you here you have a relative minimum. And you know based on the second order derivative, a relative minimum has a positive value, relative maximum has a negative value. But let's erase this, and we've identified a relative minimum and relative max. We're finding an inflection point. How can you do that? Look right over here and pick out points. We're looking here only at signs, we're not looking at actual numericals. If I put a 0 over here, all the signs I'll put over here will be based on the second order derivative, and everything based on this equation. If I'm putting a value here of 0 in there, I'll get a 0 over here. We're just putting signs here based on this. If I put a 45 here in this, I'll get a minus value, because you're just going to do 45, you'll sign it, but there's a minus here, so it becomes a minus. At 90, we don't have to look at these apexes or the zeniths, we're only looking at the points in between. The next point I'm going to jump into is 135. I do 135 sine and I have a minus. Here I'm seeing a minus over here. Then I'm picking my next point of 180. You know sine of 180 is a 0. We might as well just put that. Whether it's minus or positive, it's generating a 0. My next point here is 225. When I do 225 and I sine it, I'm getting a minus, but my second order derivative already has a minus, so it makes it a positive. I'm seeing a positive here. We're not looking at the apex or the zeniths, we're looking at everything else. Here I'm looking at a 315. When I do 315 and I sine it, I have a minus, but then that minus negates it and makes it a positive. At this point, you know you're going to have a 0. You know this curve would technically continue here, and this curve would technically continue here. Now you have to look. If you were to pick a point right over here, it would very well be a positive. If you were to pick a point right over here, in between, another 45 degree angle right here would be minus. Look where you're seeing a change from a positive to a minus in terms of your second order derivative. All these signs are second order derivatives. If you don't accept the fact that I've approximated these values here in the shaded portion, we can do that. We can pick a minus 45, we can do 45 minus. We'll put everything right here. We have a sign and then we have a minus, and it brings us that positive. We can do a 45 degree angle right after 360, and we can do sine of that. I'm getting a positive, but that positive is converted into a minus, and there it is. All your signs are here, and let me circle them out for you here. Everything from here will be used to determine inflection point behavior. Wherever you have a change in your second order derivative from a positive to minus or a minus to a positive is where the inflection point exists. From here we have a positive, here we have a minus, and right here is our first inflection point, which is 0 degrees. Our next inflection point is right here from a minus to a positive. It occurs right here at pi. My pi is my next inflection point, and you know here will be pi comma 0, this will be 0 comma 0, and here we're going from a positive to a minus. My inflection point right here is at 2 pi, it will be 2 pi comma 0. So in this area right here I'm seeing 3 inflection points. I have a 2 pi comma 0, I have pi comma 0, and I have a 0 comma 0, and that's where you're seeing the second order derivative demonstrate a change in a sign, either from a positive to a minus, minus to a positive. But you can do a similar exercise for any other function so long as it's continuous and so long as it's differentiable over that interval. Your main takeaway message here for the inflection point is where your second order derivative will change sign, and that exactly is where your inflection point will exist. This is everything here with regards to the second order derivative. Thank you for watching. Have a nice day.